Start, can I ask a question?
Yeah, go ahead. What's up?
So on the test yesterday,
Yeah.
there was a question where you asked to solve using a trig sub,
Mhm.
and when we got down to the very bottom, there was the bonus. If we had a question that we wanted to solve as a bonus, do we have to use the same instructions that were above it, or would we be able to use a different method in order to solve it, and it still counts as the bonus question?
It needs to be using the directions that are on the exam.
Okay.
All right. Well, folks, welcome to Thursday class. I just checked Canvas and it seems like everyone has turned in their exams, so that's great. My afternoon will be filled with looking at all of your wonderful work, okay? So my goal is to get exams back to folks. I think tomorrow might be a little unrealistic because there are about 60 of us, but my hope is that by Saturday at the latest, you'll have your grades back, okay, for the exams. I know the exams carry more weight than the quizzes, but it's also a cumulative section. And of course, we want to know how we did on that. So please be on the lookout for your grades to be posted anytime today, tomorrow, or Saturday. Okay. If you have any please make sure that you take a look at what I graded, just because I think some folks, I'm leaving some feedback in there and I just want to make sure that folks are seeing the feedback. I don't want you to just see the grade and be like, oh, okay, but maybe just go in there and kind of see like what's going well, what's not going as well, and how you can kind of make changes for the upcoming lesson, okay? I did want to just start by taking a look at Canvas today. So I'm going to go ahead and share my screen. Okay. So on Canvas, all right, the logistics button is still in the same place, but for whatever the new sections are, I'm going to move them to the top. So for example, we're starting chapter 10 today. Exam 2 will cover chapters 10 and chapter 12. So I've moved both chapter 10 and 12 to the top. You should be able to see in the same format that everything was for chapter 9. You'll have all of the sections, and then within each section, you'll find blank notes, complete notes, as well as the link for the videos. So chapter 10 is here, chapter 12 is here, so you can kind of preview what kind of content is coming up. Chapter 10 is probably new for most everyone, and chapter 12 is going to be a blend of review. So depending on when you took pre-calc, parabolas, ellipses, and hyperbolas were definitely part of the pre-calc curriculum. So that might be review for you, which will be kind of nice if it is, get a little bit of a breather. But 12.5, I think, tends to be new for everyone. Okay, so the next two sections that we're going to talk about, some of it's going to be new, some of it is going to be review for you, but just make sure to take the time to work through all the quizzes and prepare for those exams in the same way. Okay. I believe I have through quiz 8 posted already, so if you want to work ahead, you're welcome to do that as well. But I also think by now we pretty much know where things are in Canvas, so if you have any questions, definitely reach out to me or a classmate if you're not sure where to find things, okay? All right, so I'm going to stop this share. So today we're going to be covering sections 10.1 and 10.2. And so someone asked a question, are the rest of the blank notes available? I think maybe through 13.2 is as far as I've gotten, but not for the rest of the summer. I'm still working on that. Okay. There should be blank notes for 10.1 today, though. So if you want to go ahead and open that up, we're going to be taking a look at 10.1 and 10.2. So in between the two, I will stop the video. So you'll have one video that's for 10.1, and then you'll have a separate video for 10.2. Okay. Are there any other questions before we get started today? So let's go ahead and get started. Thanks, Jorge. All right. So we're going to go ahead and get started with 10.1, okay? So 10.1 is something called indeterminate forms. And in 10.2, we're going to learn about more indeterminate forms. And in total, there'll be 4 different types, okay? So one of the things I want us to think about as we work through these problems and as you work through the quiz that's due tomorrow morning is thinking about, again, that decision making. Okay, so how do we know what method to use? Because we're going to learn a few different methods today. And in addition to that, how do we know as we're working through a problem if we need to use some of the other methods to help us out? So again, we might need more than one method to help us solve any given problem. Okay. So in section 10.1, we're actually doing a little bit of a, oh, how perfect, it's Thursday, Throwback Thursday to when you first started Calc 1 and you learned about limits, okay? So what we know, we're gonna go ahead and start with these 2 questions right here, okay? So let's take a look at this first question. It says the limit as x approaches 1 of 8x cubed minus 1 over 2x minus 1, okay? So one of the first things that I hope you learned in calculus was that when you have limits and you're trying to find out what that limit is, one of the first things that you should always try is to just substitute in the number. And so we're going to do that for this particular question, all right? Everywhere we see an x, we're going to go ahead and replace it with the number 1. And so we'll get 8 times 1 cubed minus 1 over 2 times 1 minus 1. And let's see what that gets us. 8 minus 1 over 2 minus 1, which gives us 7 over 1, which we can say is 7, okay? So that was sort of like our most basic type of limit question, which is you just plug in the number and hope that you can get a number out, okay? Now I know you also learned a lot of other techniques on how to find limits, but this is kind of like our U-sub, it's like our go-to tool. What is the first thing that we should try to make our lives easier? Try substituting, because if it works, it's gonna save us a lot of that other work that we don't need. All right, so let's take a look at this other example next to it, okay? So the problem looks almost exactly the same. The function is the same, but the one thing that is different is we're plugging in a 1/2 everywhere we see the x, all right? So let's try that out. Let's plug in the 1/2, see what we get. So we get 8 times 1/2 cubed minus 1 over 2 times 1/2 minus 1. And this is going to give me 8 times 1/8 minus 1 over 1 minus 1, or I get 0 over 0, okay? Now 0 over 0 is one of the indeterminate forms that we're going to talk about today. Okay, so when you plug in a number and you end up with 0 over 0, okay, so you have to have a 0 on the top and you have to have a 0 on the bottom. In that case, we had to solve this a different way. And in Calc 1, the way that we approached this was we would factor. So we would say the limit as x approaches 1/2, and we would factor the numerator. And in this case, 8x cubed minus 1 factors into 2x minus 1 times 4x squared plus 2x plus 1, okay? Now that's one of the cubic factoring rules. It's definitely a nice one to know, a difference of cubes, but you could also use synthetic division to find this as well, okay? So we get these two, and the nice thing about this is when I factor, I realize that I have one factor on the top and it is the same as the other factor on the bottom, so those two are going to reduce to 1. And so now what I'm doing is I'm plugging in 1/2, but I'm plugging it in to the remainder of the expression. So that's going to give me 4 times 1/2 squared plus 2 times 1/2 plus 1, or 1 plus 1 plus 1, which gives us a total of 3. Okay? So the first case we had, we just tried plugging in the number, totally fine. If it's totally fine, then you can just solve that question by plugging in the number. You don't need to do anything else, okay? So the case on the left-hand side is just a substitute in, you're good to go. But the case on the right-hand side does require us to factor, okay? Now, for some of us, factoring is still a little bit of a challenge, and if you are one of those people, I would say it is not too late. It is never too late to learn how to factor, and it is an incredibly useful skill for you to master, okay? So after we factored, we were able to have a situation where we could plug in the number and try it again. And after we did that, we were able to get a value. So let me ask you folks a question. What do our answers represent? Like this 7 and this 3, what do they represent?
As x approaches 1/2, the limit of the equation 3, or y, these 3, I believe, something like that. I don't remember.
Yeah, exactly. So let's take a look at this first case. What this means is as x gets close to 1, the y value gets close to 7. Okay, so if you look at the graph, the point 1 comma 7 should be on the graph. Now on the flip side though, we don't want to see what happens as x gets close to 1. We're looking at what happens when you get close to 1/2. And it turns out that there's actually a hole in the graph there, okay? So this is that common factor in the top and the bottom, that there's actually a hole at x equals 1/2. And that's why when we plugged it in, we ended up with this indeterminate form, okay? And so this value 3 then, it doesn't represent the y value that's there, it represents the y value that the function gets really close to, okay? So as you get to like 1/2 from the left and 1/2 from the right, the y values get really close to 3, okay? All right, so that was a refresher on limits, but what's new, okay? So some folks may have learned this process in Calc 1, and so now we're gonna talk about what this new process is. So if you take your numbers, your x value, and you plug it in, and you end up with 0/0, okay? So if this happens, then what we can do is we can keep our limit, and we're going to take the derivative of the top, and then separately we're going to take the derivative of the bottom. So we're not doing quotient rule here, but we're treating 8x cubed minus 1 like its own function, and we're treating 2x minus 1 as its own function. So the derivative of the top is going to be 24x squared. And then the derivative of the bottom is going to be 2. Okay? So I took the derivative of the top, took the derivative of the bottom, and now I'm going to plug in 1/2. So I've got a 12 and a 1. So I have 12 times 1/2 squared, which is 12 times 1/4, which is 3. Okay? So same question, same answer, 2 different methods. All right, one using factoring, and then the other using a new rule that we're going to talk about. Okay? I thought I saw in the chat a question about answers in a particular format. So with our limits, we're looking for the numerical value at the end. So it's okay if you just have a number at the end, that's okay. All right, so here's the rule. The rule is called Lhopitals Rule. All right, some books have it with the S, okay? And some textbooks have it like this, okay? Both of them refer to the same rule, and we say this, we call it Lhopitals Rule. So suppose that we have one of the following cases. The limit as x approaches a of one function over another function gives you 0 over 0, okay? Or you end up with a situation where you have infinity over infinity, okay? And it could be positive infinity or negative infinity, it doesn't matter. But when we have one of these cases, the way we can handle it is using Lhopitals Rule. And Lhopitals Rule says that all we're gonna do is take the limit and then take the derivative of the top and then the derivative of the bottom and then try plugging in our numbers again, okay? So some problems we're gonna see, we only need to use Lhopitals one time. But there might also be other questions where we're gonna have to use Lhopitals Rule more than one time, like keep taking the derivatives until we get to a situation where when we plug in our number, we actually get a numerical answer, okay? But here's the deal. You can only use this rule when you have a 0 over 0 or a plus or minus infinity over plus and minus infinity. If that's not the case, you cannot use this rule, okay? So that's something I just really want to emphasize because I think sometimes we are like, oh, we have this rule, I can use it all the time, and that's not always true, okay? So this is for one of our indeterminate forms. All right. So we have 5 different examples here for us to take a look at, okay? So we're gonna go ahead and get started with this one. And we're actually going to do this problem 2 different ways, all right? We're gonna do this the long way, and then we're going to see if we can use Lhopitals Rule, and that should be shorter, all right? But I want us to know that there's more than one way to answer the question, and then why we're allowed to use Lhopitals Rule here, okay? So the first thing I do with any limit question is I take the value they give me for x and I plug it into the equation and see what happens, right? Because again, I don't want to do more work than I have to. So I get cosine of 0 plus 2 times 0 minus 1 over 3 times 0. Well, this looks good because the denominator is going to be 0, so that's promising. Cosine of 0 is 1, so plus 0 minus 1 gives me 0 over 0. Okay, so I've got the 0 over 0. That means that I could use Lhopitals Rule. Okay, so that's going to be our second method, but like I said, we're going to kind of go the long way first just to get some practice on some foundational limit calculation, okay? So one way we could approach this problem is we can take the expression that we have and move it in or split it up into different fractions, okay? So what I'm going to do is I'm going to take cosine x minus 1 and make that the numerator for one fraction, and that denominator will be 3x. And then I'm going to make the other fraction be the 2x over 3x. Okay, so all I've done is split the fraction. Now, what that gives me is the limit as x approaches 0, okay? Now, with this last term, I already can see that this x and this x reduce. So at the end, I'm going to have a 2/3, okay? But let's see what happens to this cosine minus 1 over 3x. So we're going to make some trig substitutions, and we're going to multiply by some things. And so what we're going to do is we're going to take this we're going to take this 3 and make it a 1/3 in the front. And that's going to leave us with cosine x minus 1 over x, and then plus the 2/3. Okay. Now I'm going to take this cosine x minus 1 over x, and I'm going to multiply it by its conjugate. So that's going to give me 1/3 times cosine x minus 1 over x times the conjugate of cosine x minus 1 is cosine x plus 1 over cosine x plus 1, and then plus 2/3. Okay. Now what this allows us to do is we can take the numerators and multiply them. And so we're going to end up with a numerator of cosine squared minus 1. And then our denominator will just have x times cosine x plus 1, and then that plus 2/3. Okay. Now, what I can do with this cosine squared x minus 1 is I can actually replace that with sine squared, okay? So I'm going to take sine squared and replace it with my cosine squared minus 1. Okay. And now I'm going to resplit this into 2 fractions. So what I mean by that is I'm going to have 1/3 times, I'm going to take one of those sine x's and put it over the x. And then I'm going to keep the other sine x and have that over cosine x plus 1, and then plus 2/3. Okay. Now, one of the trig functions that you learned about in Calc 1 in terms of limits was when you have sine x over x, that goes to 1. Okay. And when I plug in 0 over here for the second fraction, sine of 0 is 0. So this whole term goes to 0. Okay. Now what I really have then is 1 times 0, which is 0, times 1/3, which is 0. So I really end up with the limit as x approaches 0 of 2/3. And that means that everywhere I see an x, I plug in 0, but there's no x, so it's just going to be 2/3.
I have a question.
Yes.
Because weren't we supposed to find the derivative of the function?
We're not using Lhopitals yet.
Oh, okay.
Okay. Yes, there's actually a correction here. This should be a negative sine squared, and so we'll make this a negative, and that's still going to go away to 0, and we'll still end up with the 2/3. But good catch there. Okay, So this was the way that you knew how to handle it in Calc 1, right? A lot of algebra, a lot of trig substitutions, knowing your trig values, and really, really long. And so now we're going to try using Lhopitals and see how that goes, okay? Now again, I know I can use Lhopitals because this is 0 over 0. If it's not 0 over 0, I can't use Lhopitals, all right? So if it's like 0 over 5, can't use Lhopitals. If I plug in the number and I actually get a number out, can't use Lhopitals, okay? So it's not an all the time kind of thing. It's when it's 0 over 0 or infinity over infinity. So if we are going to use Lhopitals, let's go ahead and take those derivatives. So let's start with the denominator. That's a pretty straightforward one. The derivative of 3x is 3, right? What do we get for the derivative of the numerator?
Negative sine x plus 2.
Negative sine x plus 2. Beautiful. Okay. So we tried Lhopitals. We took the derivatives one time. Now we try plugging in the number again. So we get negative sine 0 plus 2 over 3. Sine of 0 is 0. So this goes to 0. And I end up with 2/3. Okay. So same answer that I got the long way, but in a different method. Okay. So that's actually a really interesting point to bring up. I know some of you on the exam were like, well, I think it would be easier this other way. And yes, there are certain strategies that are certainly easier than others, and that is part of that decision-making process. But if I ask you for the long way and you can do it the short way, you already know what the answer is going to be. It's already like a built-in answer key for yourself. You kind of know, you're like, I know the answer should be 2/3. Let me figure out how I can try and get 2/3 using this other method. Okay, so this is the longest example that we'll have for 10.1. Okay, so I just wanted to do this one as this idea that there are often more than one way to solve a problem, but in this lesson, we're focusing on this second column, this Lhopitals rule, all right? So let's move on, okay? Let's take a look at example number 2 here. So I've got the limit as x approaches 0 of this function. I'd like you to go ahead and plug in 0, see what happens, and confirm that this is a case where you need to use Lhopitals. All right, so if you are going to use Lhopitals, I want to see that confirmation. How do you know that you can use it? I may have you do the long way on a quiz or an exam. Yes, that's definitely fair game. All right, so just by plugging in 0, this is what I get. E to the 0 gives us what value?
1.
1, good. Plus e to the negative 0?
1.
1, so 1 plus 1 minus 2. All right, and then cosine of 0?
Is 0. I mean 1, sorry.
It's 1, yeah. All right, so I've got 0 over 0, so then I know I can use Lhopitals. Yes, all right, so thank you for looking ahead to the quiz. If you haven't started doing that, I think that's actually a really good idea to start looking at the quiz as a way to kind of see what kind of content is coming up. But Carlos's question was, when you say find the indeterminate form, do you want us to plug in and show that we get 0 over 0? Yes. So in 10.2, we're going to learn some other ways. So there are other indeterminate forms, but I want to know which one you're using, okay? Okay. So we've got our 0 over 0. That means we can use Lhopitals. So let's go ahead and start taking derivatives. All right. Derivative of e to the x. 10.1, 10.2. E to the x. All right, derivative of e to the negative x.
Negative e to the negative x.
Negative e to the negative x, derivative of minus 2.
0.
0, okay. You don't have to write that plus 0, you really don't. I am writing it right here just so nobody thinks that it went away. All right, derivative of 1 on the bottom.
0.
0. Derivative of negative cosine 2x.
Negative 2 sine of x. 2x.
Yeah, it's going to be minus that negative, and then we have to use chain rule, so 2 sine 2x. Okay. All right, let's try plugging in 0 again, see what happens. E to the 0 minus e to the negative 0 over 2 sine of 2 times 0. Okay. E to the 0 is 1 minus e to the negative 0 is 1. Sine of 0?
0.
0. So I get a 0 on the bottom. 0 over 0. This is an example where you're going to have to use Lhopitals more than one time. Okay? So you do it once, plug in your numbers. If you get a number out, that's awesome. That's your answer. But if you get 0 over 0 again or infinity over infinity, you got to use Lhopitals again. So we're going to take our previous derivative and take another derivative. So e to the x is e to the x, and then this becomes plus e to the negative x. And the derivative of 2 sine 2x?
4 cosine of 2x.
4 cosine 2x. Very good. And so let's try plugging in our numbers again. E to the 0 plus e to the 0 over 4 cosine 2 times 0. And so I get 1 plus 1 on the top. That's promising. And then 4 cosine 0 on the bottom. Cosine 0 is 1. So I end up with 2 over 4, or a final answer of 1/2. Okay. So here's what this means. If I graph my initial function, okay, so if you throw that function on Desmos and graph it, if you zoom into the x value of 0, the function should get really close to a y value of 1/2. Okay? All right. Any questions on example 1 or example 2?
Is there a way to, by just looking at this one, that you know you're going to use it twice?
I don't know that there's a rule necessarily. I think that's why it's important to know like why you're taking another derivative. Does that make sense?
Yeah.
Okay.
Thank you.
You're welcome. All right. So let's do this. Let's have you guys try example 3 and example 4. Okay. So again, on the quiz, there's directions that say, you know, find the indeterminate form. So that's the part where you plug in the numbers, see what you get, and then that tells you, as well as me, but more importantly, you, what strategy you can try with that. Okay. So I'll give you guys a couple minutes to try example 3 and example 4, and then we'll check our answers there. All right. So if we take a look back at the screen, all I've done so far is plug in the infinities that they asked me to plug in. And in both cases, I ended up with an infinity over infinity, okay? So for both cases, I know that I can use L'Hopital. So let's take a look at example 3 first. All right. Derivative of the natural log of x. What do we get?
1 over x.
1 over x, very nice. And that's something that we've seen, especially with our integration by parts, right? That was our, if we see a natural log, we knew we had to choose that as our u, and so that helps us practice that derivative a little bit, right? So we've got 1 over x. Now, this one over here, I just want to rewrite as x to the 1/2, okay? And so when I take the derivative of x to the 1/2, I'm going to get 1/2 x to the negative 1/2. But this is going to be significantly easier if I write it using square roots. And so I would do that by saying this is the same as 1 over 2 root x.
You write it as 1 over 2x to the 1/2?
The square root, I think, is going to be more helpful in simplifying. But either way is fine. I think more traditionally it's the 1 over 2 root x. But that would go over here, okay? And so let's plug in our infinities again and see what we get. We get 1 over infinity over 1 over 2 square root of infinity. 1 over infinity, what does that go to?
0.
Goes to 0. And what about 1 over 2, the square root of infinity?
0.
Also 0. Okay, so like number 2, this is a case where we're going to have to use L'Hopitals more than one time. So let's take another derivative. Derivative of, actually, wait, sorry. So for this one, if we wanted to simplify this a little bit more, we could write this as 1 over x times the reciprocal of the bottom, right? Because dividing by a fraction is like multiplying by the reciprocal. And when we do that, if we simplify this a little bit more, we're going to end up with 2 over the square root of x, okay? Because this square root of x and this x reduce to a square root of x on the bottom. And now let's try plugging in our numbers again. 2 over square root of infinity. And what does that give us?
0. 0.
Yeah, this gives us 0. So guess what, folks? This question has an answer of 0. And so the reason why I chose this question is because I think a lot of times we're like, oh, if I see 0 on the top, then I'm going to use L'Hopitals. But the reality is you have to check, it has to be a 0 on the top and a 0 on the bottom, okay? So 0 on the top and 0 on the bottom. But if you get 0, that's an okay answer. It's okay for a function to be approaching 0 as a y value. It is x to the negative 1/2, but I wrote it on the bottom, so it's already to the negative 1/2. That make sense? No, there was no rationalization.
Wait, so Professor, if we did it the first way and got 0 over 0, how would we know to simplify it the second way and get a 0?
because it's probably, that's why I'm highlighting this question, right? We could continue to take derivatives, but we should always kind of see like, what can I simplify first? Is there another way to write this so that I don't have to keep going? All right, let me just do this part again real quick because I think some of us are a little confused where things came from. When I have the square root of x on the top, that's like the square root of x, but an x on the bottom, I could write that as square root of x times square root of x over square root of x. And so when I reduce, I get 1 square root on the bottom.
The way I do it, I do
That's
x.
where this comes from.
The way I write it is I put x to the 1/2 on the top, and I put x 2 over 2, and then I just like, you know.
Perfect. That is fine as well. If you want to work with the fractional exponents or just with the radicals, both ways work. Okay. Any other questions about number 3?
So the first time you take Lhopitals, could you also simplify that fraction over a fraction and then plug the limit in that way? Because I did that instead and got infinity over infinity, so it tells you to use Lhopitals again, but I don't know if that's like appropriate.
Wait, what do you mean?
So if you simplify like the 1 over x over the 1 over 2 root x, you would get 2 root x over x. And then if you plug in the infinities into that, you would get infinity over infinity, right? Which tells you to use Lhopitals again. Could you do that, or would you rather leave it in that complex fraction?
I would see if you can reduce things first.
Okay.
Yeah, so I think the overarching strategy is like, we like to use calculus for some things because it makes it easier, but a lot of times by algebraically simplifying things, we can actually avoid using the calculus. Okay. All right. So let's take a look at example 4, okay? So again, we plug in the numbers, we get infinity over infinity, and so that's our cue that we should try Lhopitals, okay? So derivative of the bottom is just gonna be 2x, but what do we get for the derivative of the top there?
Three.
Yeah, we're gonna have to use a little bit of chain rule there, right? 3e to the 3x. And so let's plug in our infinities again, and we're gonna end up with 3e to the 3 infinity over 2 infinity, which is gonna give me infinity over infinity, okay? And there's not anything that I can simplify here, which is different than example 3, right? So I kind of do that check. Is there anything else that I can simplify? And if not, then I try Lhopitals again, okay? So maybe that's a better way of phrasing that decision making for example 3, right? I tried Lhopitals once, but I saw I could simplify some things, so I chose to do that before trying Lhopitals again. But in this case, for example 4, we're kind of forced to do Lhopitals again. So let's take a second derivative. The bottom is going to be 2. And what's the top going to be?
9e to the 3x.
9e to the 3x. Okay. So we plug in our infinities. And we end up with what as our answer?
Infinity over 2.
Yeah, we end up with infinity for an answer, okay? Now, it's infinity and not infinity over 2 because infinity is so large that it's the same as infinity over 2, okay? And so when we're looking at this, again, the reason why I chose this question as well as number 3, is because I want us to be okay with an answer being 0 or an answer being infinity, okay? So an answer of 0 is not bad, it's not wrong. And an answer of infinity is not bad, it's not wrong, okay? And the only times when we're gonna need to use Lhopitals is when we have a 0 over 0 and an infinity over infinity. So it's gotta be in top and bottom. It can't just be in one of them, okay? All right, so we got one last question here, all right? So I'll give you folks a few minutes to get started on this one, see what you get. And then we'll kind of talk about the strategy and the reasoning for this particular question. All right, so where did folks start with this? What did people do first?
Plug
Direct
0 in for x.
Yeah, plug 0 in. So we've got e to the 0 plus e to the negative 0 over 0 squared. So I've got 1 plus 1 over 0, or 2 over 0. All right. What's another way to write 2 over 0?
Infinitive.
Yeah, 2 over 0 is infinity. Okay. So in this case, if I look very specifically at this fraction right here, is this a case for Lhopitals?
No.
No, this is not a case for Lhopitals because I have a number over 0. I do not have 0 over 0. I do not have infinity over infinity. So our answer here is infinity, and we should not use L'Hopital, okay? Now, if you did use L'Hopitals, all right, let's just show that if we did use it, we would get a different answer. So let's say you were not paying attention. You're like, I don't know, I like that thing where I take derivatives. So I get e to the x minus e to the negative x over 2x. And that's going to give me 0 over 0. So then I try L'Hopitals again. And I end up with e to the x plus e to the negative x over 2, which would give me 1/2. And you're like, oh, my answer's 1/2. Sorry, there's definitely a lag today. I'll try and figure this out during the break. This answer in the red is not correct because we cannot use L'Hopitals anytime we want to or anytime we see a fraction. It has to be a very specific case, 0 over 0 or infinity over infinity, okay? So this is a do not do this.
Shouldn't that be 1?
Yep, it should be 1, you're right. Do not do that either. Okay, there we go. All right, so folks, this is it for 10.1. So I'm gonna stop the video here and we're also gonna take a break. And then when we come back, we'll be starting with 10.2, okay?